All right, everyone. Welcome to life science stream about infrageometry. We have here today Nick and Uti with us. So welcome, Nick. Welcome, Uti. So today we're going to have a more of an informal presentation on the state of the research, and we're going to do some free-form work session on infrageometry. The goal for me today is to try to understand what could be the role of rewriting rules in the current instance of the infrageometry project. Last week, on Friday, if I remember correctly, we had a live stream with Stephen Wolfram. So if you head over to the Wolfram YouTube channel, you can catch up with the sort of more complete explanation and presentation of the infrageometry project. I'll do a summary in a minute. There you could see sort of the scope of the project and the main questions that we are addressing. Today, I want to, at that meeting, I didn't have the time to express and to present some potential interaction between sort of multi-computation, hypergraph rewriting, and this infrageometry sort of set of ideas. And hopefully I'll be able to make a case for an interesting crossover, which is a very sort of appropriate branding for an institute project at the end of the day. So without further ado, let me share my notebook here so you can get a summary of the infrageometry project. Okay, so actually let me double check that everything is running technically okay. Seems good. We're in YouTube. Let me see. Just to make sure that I'm not missing any messages. Yeah, all looking good on the YouTube front. So yeah, the infrageometry project, generally speaking, is a set of little ideas, little projects that we're trying to put together to develop a formal theory that encompasses both continuous and discrete manifolds. So as many of you know, in the Wolfram Physics project, there's this idea that we can model the universe and physical structures in the universe based on discrete combinatorial structures or hypergraphs that will somehow give a discrete account or a discrete approximation to a continuous limit of what we are familiar with in general relativity, quantum mechanics, etc., with the use of smooth manifolds or continuous spaces and things like that. So the goals here are to both provide a template for a rigorous context where the claims of the Wolfram Physics project can be tested, because many of these claims are purely in typical Stephen Wolfram style, sort of given out as sort of hopeful claims and very interesting claims. But to have a formal framework to test them, we need some overarching theories, and then we also wanted to see if we can recast the usual theory of manifolds, the usual language of physics, of modern physics, which has to do with manifolds and the fields of real numbers over these manifolds, and the associated modules and algebras and tensor products and all these kinds of language that is heavily used and has been used with great success in the last century or so. We wanted to see if we could recast all this formalism in a language that is more native to something like a hypergraph, generative hypergraph rewrite system, which is what already has been investigated in the physics project. So the core idea that Jonathan and I try to deepen from some of Stephen's comments originally has to do with correspondence between graph or graphic structures and geometry, differential geometry. So the basic idea is that you want to think of the points. So I'll just go straight to this particular example. So you want to think of the points in a discrete set. You want to think of the elements of a discrete set as the points of a space or manifold, and you want to think of graphic structures on such a set of points, such a set of elements, as the connectivity structure of those points, something that gives you simultaneously a measure of distance, simultaneously a measure of separation, simultaneously a measure or a notion of direction, betweenness, etc. So many of the geometric notions that you're familiar with in affine geometry or differential geometry or Euclidean geometry, you can see in a condensed, somehow discretized way in this way. So the presentation that we had last week focused on what we call the tangent structure, and I think the tangent structure is probably one of the most naturally geometric things to look at in a manifold, perhaps together with something like a metric structure, which is in fact very closely related to the tangent structure. So here's a little presentation of how the tangent structure looks like in our context. So first of all, we think of the data of a manifold, the data of a space would be some graphic structure in a set of vertices, right? So in what in mathematics we would call a hypergraph, right? In general, so some combination of edges of arbitrary orders in principle that will be the data of a space on a given set of points. So in a particular case, the simplest case in a way, where we just take an undirected graph as our graphic data, we can think of it as the manifold, and then we can think of the tangent space of that manifold as simply the length one paths of that are possible in that space. The reason why we take length one paths is because we are taking the analogy that tangent vectors are infinitesimal curves, or equivalent classes of tangent infinitesimal curves at a point. So in a way, the smallest curve that we can have in a graph is a length one path, right? It's an entire directed edge between two vertices. So the tangent bundle would look like this. Basically, you take all the pairwise undirected edges and you double them with directed edges. And of course, the tangent space at a point will just be the collection of edges that are outgoing from any given vertex. Naturally, a vector field will be a choice of such directed edges for each vertex. And then if you want to start developing something that looks like the vector calculus or the tensor calculus of a manifold, then you need to start thinking about the functions on the space, not only the paths on the space, but also the functions on the space. So the notion of a function in the space is quite simple. You just think of, pick your favorite field of numbers, f, and just evaluate some function on the set of points. So a function in principle has no information about the graph, right? So in principle, the function is tied to the points, and that's to say that in a manifold, functions, you can just take the set of points in a manifold, and you have functions defined there. It might be interesting to consider, and I'll make this a little note here. So, oops. So I'm going to make a little note. So what is the analog of continuity, smoothness? For
Does it have to be a number field? Can it be more general?
Like well, it can be more general, but for this is just to recover the notion of function proper. Of course, you can have a more general assignment to any kind of algebraic object, right?
Yeah, because I've seen some examples and in geometric algebra or geometric calculus in this case, when you have at every point of the manifold you assign basically a pseudoscalar or an element of it.
Exactly. So I mean, well, that's what I find interesting, that in the traditional, at least the way I understand differential geometry, the way I learned and I taught differential geometry at university, you think of the space as having the connectivity structure basically being the topology. So you have points and open sets and all this kind of machinery, and then you define things like curves, and you define things like functions, which can actually be local curves and local functions. You don't have to have any global sort of sense. And out of those, you can very naturally define what tangent vectors are and cotangent vectors are, and then you define at every point a tangent space and its dual and all the tensor powers of these. And so you have effectively a range of possible tensor valued things at every point of your space, simply by the definition of a curve and the definition of a function, right? That together with the smooth structure or continuous structure of your manifold basically completely determines uniquely all that piece of data. So that's why I'm focusing here on sort of scalar functions and paths, because it's kind of like the.
So is there a simple dual representation too, or you have to like also talk about derivatives later?
Well, yes, exactly.
To describe your dual notion of the tangent bundle. Right?
Exactly. Yeah. So anyway, I just made this note here because I realized that. So why? So let me explain this point here. So okay, so a vector field. So a vector field is an assignment of basically a subgraph, if you want to be very general. It's a subgraph of your tangent graph, let's call it. And but it has a constraint for it to be a vector field. Basically, the constraint is that you have one tail per vertex, and that's it, right? So there's a well-defined flow. You could almost think of this as some kind of map from vertices to vertices, not necessarily a permutation, but some kind of map, right? So
what if there's no edges from the vertex? Is it allowed to have like this free floating vertices to define your manifold?
You mean a vertex like just floating here?
Yeah. No edges, incoming or outgoing edges. Like this kind of graph. It's still.
I would say so. I would say that. Yeah, I would say that's the no edge could be the zero edge in the analog of in the continuous analog. You could think of. I mean, having a vertex floating just means that you have a disconnected manifold. That's fine, right? There's no problem there.
Yeah, and you can define a vector field on it. It's like it's undefined at this point, right? Basically, if you
that, or it's the zero value. So the zero curve, right? The zero curve in if you think of curves as something that allow you to compute a tangent, right? So and the tangent is what defines a tangent vector, then the zero vector is not a vector in that definition, right? Because it's not a tangent. It doesn't have a well-defined tangent, right?
Oh yeah. Well, can you can you make this choice at any point? Then it's like not just the ongoing edge, but you can. There's also a choice for zero at this point.
So Nick is right. I mean, so I was looking at that, and it turns out that that a vector field determines an algebra homomorphism of functions on the graph. And if you have the identity algebra homomorphism, then the vector field corresponds to just like the zero vector field. At each point you have the zero vector, and the vector field associated to that algebra homomorphism is just like cyclic edges. Like at each point you have an edge at that point.
I think Nick's question is slightly different, though. I think Nick is asking more about isolated vertices. Isn't that right?
Well, not just that. I also ask whether you don't have isolated vertices, but also as a choice of your vector field, can you choose a cycle basically at any point as this?
A self. Oh, I mean, I see what you mean, like a self edge.
Yeah.
Maybe
your tangent bundles also should include each vertex.
We should be able to do that. Like otherwise, we couldn't define zero vectors.
Okay. No directed edge self as.
You can also think of it as soon as you end up in that point, you kind of stay there because you don't have any choice. It's like multiplying by zero. So it's like
right.
Maybe.
Yeah. Well, that's interesting. Yeah, actually, that's true. Yeah, that's a possibility. I guess it could be merely a matter of convention. In what we have this ongoing. There's always this kind of freedom to either be simple hypergraphs and make sure that you're labeling things in certain ways, or you allow for self loops, and therefore you allow for these kinds of situations. In my opinion, it makes sense to have a self loop here a lot, right?
Yeah, it just kind of makes a degenerate vector field of some sort, right?
To be honest,
Maybe.
now that I think about it, it depends. Yeah. So, yeah, it actually, I mean, I was going to say that I wanted to retract my words, but I don't really disagree with myself in the sense that I see that if you see vector fields as flows, then definitely we need self edges, right? Because it's perfectly fine that a flow just keeps a point invariant, right? It keeps some point fixed.
It's like a sink.
Exactly, like a sink, a stable point, right? Sink or a source, right? But it could be some stable point, some critical point, right? So I think that it makes sense that we think of those as self loops because, you know, as a flow that's well defined, it's just saying come back to the same point, right? Now, and you could definitely have like the problem is you can have a sink, like you say, but you by our definition, it's hard to see how that will be formalized as a source, right?
Yeah. Well, maybe that's some kind of dual of your vector field.
Well, but I mean, in principle, you should have vector fields that have sinks and sources, right? And things in between, like critical points that are neither.
Well, if you define it as just as a choice at each point, you only have a choice. If you choose a loop, you should always stay there.
Yeah.
So,
but what I mean is that
in this definition, basically sources and sinks are the same thing. It's not really a sink.
not necessarily, because you could, I mean, here's the asymmetry, right? You could have, I mean, I wish I was fast enough to draw a graph here. I can just use the hypergraph draw. That makes me fast enough. So you could have something like this, right? So wait. So this might be live review because I want to have it ordered. So, okay. Oops, something. It's just laggy. It's just laggy. Okay. Okay, I just reset it. It's super laggy for some reason. Okay, so I'm gonna draw ordered. So imagine that you have something like this, and then something like this, and then something like this, right? You could have, if you have a self loop there, right? That's a valid vector field, right? Because there will be an arrow. By the way, is there a way to make a loop here? I don't think so, right?
Well, I think you have to select it twice.
How do I select it twice?
I think you call some kind of button. Maybe shift. Well, try some button there's some multiple selection should create a multiple selection.
Okay.
I haven't done it in a while. I don't remember.
Okay.
Let me try it myself.
Nah. Oops.
Well, for me, it's an option.
It's an option? What do you mean?
Alt, I think, on Windows.
Oof, this is, we need to, I can't really use this because I can't undo. Can I just set? Not here.
Kind of glitchy right now. Yeah. When it loses focus. But that's basically when you make an edge with like this should work. Maybe try to press it multiple times.
But I pressed E and it's kind of crashing or something.
Can you?
E? Yep. Oh. Okay. It did it, but there was an error message there. So, okay, that's useful to know. So in Windows, I think it's Control. No, it's Alt. But why does it multi-select? Okay, now E. Yeah, it gives me some kind of error when I. Poof. And I also cannot delete by pressing delete. I don't know. Oh my gosh. Why is it so slow? Anyway, my point is you can have this situation.
It would have been faster using like some canvas at this point.
For sure.
This is bugs.
This is not going to be useful today, so I'm just gonna, because the graphics are slowing it down. Okay.
And there's too many of them opened at the same moment.
Yeah. So anyway, what can I do? Can I annotate just on the Zoom, just for to illustrate what I wanted to do? So
Well, try canvas. You just basic. Where is it? There's a button there. Let me show it to you.
Canvas? Like you mean like in here or in Zoom?
Like this one. Just try this button.
Okay. Okay, so what I meant is you can have this kind of situation, and then you can still have an arrow here, right? Because these are vertices that are coming from out of this vertex here, and so but if you have something like the same situation, you have this vertex is pointing somewhere already. I mean, I cannot have a sync here as well, right? Because that's two vectors on the same point.
Yeah.
So there's some kind of asymmetry. That's what I meant. But, you know.
Oh yeah, you basically allow to choose a loop only when the incoming edge is to that point, right?
But that's what I meant. By definition of vector field.
I mean, like you can also have two outgoing edges at any vertex, obviously, but you just choose one. So
Yeah,
in
for
the
the
second
vector
case,
field you choose one, but the whole
yeah,
tensor bundle contains all the loops and all the arrows, right?
yeah, precisely.
For sure.
Yeah.
Yeah, but yeah, I just think that the definition of vector field kind of breaks down if you try to intuitively represent a sink and a source, right? So there's a comment on YouTube. We might consider left and right orientation of the self edges. Well, there's no orientation of the self edges because they are self edges, and there's no geometry. I mean, the actual geometry of the loop is just graphics. It doesn't have any information for the orientation. So anyway, this was just a comment, but I think it's important that we keep in mind that this is something to be considered. So self edge is a zero vector. Sounds interesting. No directed edge as undefined could also be, I mean, that's natural because there's no information there, so it's undefined, so it's sort of out of the domain of the vector field. So like a partially defined vector field, that's fine. Okay, so where was I? I think this was Nick's question on how to think of self loops. Okay, so the last time what we saw is that the moment you consider functions, you can start doing some form of calculus. So instead of the construction of a directional derivative, what you can do here, the analog, is to take one oriented edge, PQ, for example, right? And basically go from, for example, this edge to this edge and say, how much does the function change? Which is to say, how is the landscape changing around me when I move from this vertex to this vertex? And the net change is I go from 0 to -1. So you're sort of going downhill in that function. So you compute the difference, the finite difference between those, and that gives you a new number. So if you assign that new number to the starting point, right? So you have, where the vectors define, you define a new function so that it's the closest analog to a directional derivative. There's some kind of instantaneous rate of change at that point. Then you define G as this delta x of f, where x is an assignment, and you can just simply compute, arithmetically for all vertices what the value of delta xf is, and therefore you have a new function. So this is now a way of assigning functions to functions. It is linear by construction. It is annihilating on constants. Obviously, if there's a constant assignment of values, then you see no change. And then most importantly, as we discussed last week, and as Uti has been delving into, they satisfy the weighted Leibniz identity, and that makes them quite unique or quite special in the usual treatment. And so when we got to this point, in this sort of rabbit hole of tangent structure, you find that the weighted derivations that correspond to some discrete vector fields have an algebra of their own, and there's a question of what does that algebra correspond to in graphic terms, right? And so we had a long debate with Jonathan and Stephen last week on exactly how to make that happen, what specific construction on the graph corresponds to adding these vectors or composing them and so on. And so obviously the goal here is to try to understand, on the continuous or smooth side of the story, you have the conventional Lie algebra vector fields, understanding vector fields as infinitesimal groups of transformations, and you have this composition of commutators so that you are closed and so on. And the idea is how to interpret that in the context of discrete derivations or finite difference operators. And well, that's an open question. I don't think there's any closed answers to that yet. So what I wanted to discuss today, what I wanted to propose, is what I call the rewriting approach, which I did mention in last week's live stream, which is in a way taking the rewriting philosophy seriously in this context. Basically, that's to say that if you have a hypergraph and you take seriously that that's the actual data that you have to work with as your analog of a smooth manifold, it should be that you're doing any kind of process, any algebraic construction, any computation calculus thing that you're doing with that graphic data should be translatable into something like hypergraph rewriting, because that's the natural language, the natural sort of operational and compositional language of hypergraphs, right? So the two examples that I had in mind were to identify the. So let me get rid of this. Were to identify the
Sorry,
difference. Go on.
Sorry to interrupt, but I mean, before you mentioned what's the analog of smooth field in this in discrete geometry?
Yeah, that's yeah. No, is that a question, or what's the question?
The question is that I have a bunch of things that I mean I did some explorations in that area about how you recover some stuff and how do you generalize it. So if you now want to talk about the rewriting approach, should we talk about that first, or should we wait for the rewriting approach to finish and then, because then we might get confused if we mix up the topics.
I was actually going to say that if we wanted to discuss something from this general perspective first. Let's discuss that, and then we can talk about the rewriting approach. So please go ahead. Yeah.
Sure. So essentially, what I'm trying to I try to do was that you define like these finite difference operators on a graph, and then so I mean the basic question I asked to myself is what would resemble a real number line. So my idea was that you just take the line, or like I kind of cheated in a way, but I drew the real number line, and then I kind of plotted points at 1, 2, 3, -1, or at all the natural numbers, and then said, okay, this is my graph. Okay, it's an infinite graph, but let's just ignore that for now.
Sure.
So I have this infinite number of points over here. So since we are like looking at since we're looking at functions on the manifold on like a graph to understand the graph itself,
Yeah.
like I tried to like say, okay, so if I take, what kind of limit should I take of the real number line, or like the discrete line, so that and so that the functions I define on this discrete line become the set of smooth functions on the real number line later on. So essentially the limit that I should take of the graph. So there's going to be like two limits. One limit is going to be the limit of the graph getting to infinity, but the more important limit would be the limit of the set of functions on the graph of the discrete graph, and I want to like make it approach the set of smooth functions on the real number line. And so there's no reason a priori that we should do that. Maybe we can just look at the limit of the graph. But since we are already dealing with these, we have this machinery of weighted derivations and stuff like that. I try to do that. And so the main thing is that the first question I try to have is that let's try to think about function interpolation, right? So if I have a function that is defined on the real number line, so what I'm trying to do essentially now is if I want that in the limit it approaches the set of smooth functions, what I'm trying to do is that on the discrete graph, I'm essentially ignoring the function in between and just looking at the function, a smooth function defined on a certain number of points, right? So if I have a smooth function on the real number line, so the analog of a smooth function on this discrete line would just be like the smooth function just defined on those values, right? So it's like I'm interpolating the smooth function by defining it on like a set of values. And so the question is, does that impose any restrictions on the functions that I can have? And the answer is no, because it's very clear that on the real number line, a smooth function can take any form. Like the set of smooth functions itself is extremely big, and so you can have like functions that are oscillating and still be smooth and so on. So there's no like algebraic restriction on the smooth function that is being interpolated on the natural numbers when defined on the real number line. There is a restriction when you have polynomials, because polynomials are incredibly restrictive. Over there, it turns out that you only need a certain number of points to determine an entire polynomial. So in that case, there would be a restriction on the graph if you wanted the set of functions on the graph to like reach the set of polynomials if I take the limit at the end. And so what I then tried to do is I tried to like kind of generalize this notion of Taylor series, because on this discrete graph, um, if I have, let's say I have 2 points, right, on any, let's say, let's forget about real number line. I draw a discrete graph, then I define a function on like, let's say, over the real numbers on 2 points on the graph. I know that if I take the limit of this graph and it's supposed to approach a smooth function, then I should be able to relate the values of the function at the next point and the function and the value of the function at the previous point by some Taylor series expansion, because because every smooth function can be expanded in Taylor series. And so essentially the idea is that every weighted derivation on the graph, which basically what's it saying? It's basically evaluating the function at the next point, at the outgoing point, subtracting it from the value of the value of the original point and dividing it by the weight. So essentially, the algebra homomorphism that this weighted derivation corresponds to is taking a point and then evaluating it at the next point. And that algebra homomorphism is determined by a vector field. And so the idea is that that thing, that operation of going from one point to the other and evaluating at that point, you should be able to do that in a Taylor series expansion sort of way. So that's like the structure that I was thinking of, maybe endowing endowing a structure on the graph by assigning every edge like a power series, by assigning an edge by some power series or something, which will tell me like the ultimate Taylor expansion. And what I think is going to be the case is that the actual power series will not matter, but like the algebraic structure of the power series would matter. So what I'm trying to do right now, like as of yesterday and now, is I'm trying to generalize what a smooth algebra is. And a smooth algebra has, like, there are various definitions of smooth algebras in literature, but I think smooth algebras are going to be extremely promising and important in this discrete geometry case, simply because in a smooth algebra, at least in this sense, there is a notion of taking taking a Taylor series expansion. And it turns out a Taylor series expansion is a very natural algebraic operation because it corresponds to an algebra homomorphism onto a power series. And so, like, that's the thing I'm talking about essentially.
I'm thinking like, is it related to just making some kind of those earlier method, Runge-Kutta method, when you just take the differences, like defining how you interpolate or maybe integrate using the earlier method, right? But when you just consider more powers in your Taylor expansion, you basically
Yes.
have more of those things together. So basically so your algebra basically generalizes all of these higher order methods of integrating from one point to another, something like this.
Yes, precisely. And there's a very good reason for why differential geometry uses smooth functions instead of like n-differentiable functions or something. The Taylor series method that differential geometry uses is very important to establish a lot of important theorems. Like Taylor series is used everywhere in differential geometry. And I wanted to figure out an algebraic, like a more fundamental motivation for it, like why are smooth functions used? And I think that, and I came up with the reason, is that the reason why smooth functions are used is because if smooth functions were not used, then there would not be a correspondence between the set of derivations on the functions and the vector fields. Like there would not be that correspondence.
Yeah.
And so I'm basically trying to generalize that, like for an arbitrary algebra, like it holds for a set of polynomials. If I consider the set of polynomials as an algebra, it holds for that. But I can actually prove that it holds for that by treating the polynomials as functions. And since polynomials are smooth functions, and it holds for smooth functions, it's also for algebras. But the proof is completely different. And so I'm trying to generalize it to algebras. Like what is a smooth algebra? Like if I have then the requirement that a smooth, like the defining feature of a smooth algebra would be that the correspondence is satisfied between like a vector field, which is an infinitesimal automorphism at every point. It should correspond to like a derivation, like a global derivation. So that's what I've been trying to do.
Yeah. No, that's interesting. I mean, that is one of the main lessons one learns when studying differential geometry, is that it seems that you have the freedom to say, okay, I'm going to make my manifold ck differentiable, right? So the up to k derivatives are continuous, right? But it turns out that if you want this fundamental theorem that tells you that the derivations of your ring of functions or your algebra of functions are isomorphic as a Lie algebra to the vector fields, geometric vector fields understood as infinitesimal groups or smooth assignments of tangent vectors, which whatever definition of tangent bundle you have, right? Then you require smoothness, right? You require that you have an arbitrary k for the top continuous derivative, right? So that's one of the things that is kind of a folklore lesson, and the main reason why you have differential geometry as a subject, which is mostly just doing C infinity manifolds, and then you have sort of synthetic versions of that and more sort of generalized versions of that in more categorical abstract sense, or you directly have geometry or analysis. There's no sort of C3 differential geometry or C27 differential geometry, right? Like there's very little life in that in between, right?
Yeah.
So there's good reason to go either just continuous, just topological, or all the way to C infinity. Like in the middle, there's, I mean, obviously a lot of work has been done, but there hasn't been sort of a great, nobody's realized, aha, 48 differentiable manifolds are particularly useful for this and that reason, right? Like it seems to be that it's either, what you gain from continuous manifolds, from topological manifolds, you have effectively all the way up until you consider the infinitely differentiable, which are the ones that have all this algebraic niceness about them and all this, the algebraic correspondence and so on. So I would recommend to you, Udi, particularly, I mean, do check the literature. There is literature on this. There has been, if I have to pull just from memory, I would say there's been work exactly what you said that you're trying to understand, of understanding the algebra of or sort of what is the smooth algebra? What are the algebras that are geometric in some sense? What are the algebras that correspond to something that would be like the sections of a bundle of some manifold, right? There is a fair amount of literature, and I think there is a fair amount of accessible literature on this, not just super technical. So do a search, or ping me later, and we can look at some of this stuff. This is definitely relevant. Now, what I wanted to take the conversation a little bit into before we go into the rewriting, because I find this question here on the screen. What is the analog of continuity or smoothness for discrete functions? I've been thinking a little bit about this, and I wanted to throw something to you, both of you. If we are taking seriously the fact that the graphic data on a set of vertices is the analog for a manifold, shouldn't we think of a function, a fully fledged function to be an assignment from edges in general to the scalars, right? When obviously, and we are thinking of the populated edges here as 0 edges, if you want, or 1 edges or something, right?
Yeah. Basically, what should you weight, vertices or edges, or both? Right?
Well, the question is, in here, I'm not saying one or the other. I'm saying just vertices or everything, because vertices in this perspective, as you remember, is you can think of it as 1 edges, right?
Yeah.
It's like the ones that are populated, the ones that you say, this is my, right?
Well, basically, then your multiplicity means the weight for everything, right? So basically, if you allow arbitrary multiplicity of edges, then vertex weight is just your 1 edges, and then all other multi-edges are just all other kind of weights on top of the edge.
Sure. Yeah, I think my point is more about whether. So absolutely, I mean that's the case where you choose your set as your field or something, and completely agree. But to me, the question is more, how would we have to modify the definition? For example, if we take this idea that a directed edge is a discrete vector field or a discrete vector, something, and now we are thinking that a function on this space is not just an assignment to vertices, but also an assignment to edges, right? It's like to say, and I'm thinking of this because of the question of what is the analog of continuity, right? So it's an assignment of values to points, but also to values of paths between points, or I don't want to say paths, I want to say between space between points, right? Like some kind of passage between points, right? So there, I mean, because here's my motivation. Why am I thinking of this? If I just have vertices with numbers on them, right, with some scalar values, I don't think you can realistically, I mean, this is just a set. So mathematically, it's very clear that there's no condition that you can impose without further information to have some kind of analog of what it means to be continuous or what it means to be smooth or something like that, right? And this is to Uti's comment that, if we are trying to develop this discrete algebra, this algebraic machinery from this discrete setting, right? The it's clear that at the level of functions, which is our first primal example of a field or some kind of assignment, something that is to be considered smooth or continuous, it's clear that we can't impose anything on functions alone, right? Because functions under this definition are just scalar assignments to vertices, right? So mathematically, there's no structure on just that. So if you think of something like, you know, bring up the canvas here, I guess. Where do I want to draw? Like here, I guess. So if you had something like, well, I can draw like that. What would I want to say? So imagine you have a dot here, you have a vertex here, and you have a vertex here, and you probably want to say something about, you know, like this as x, this is y, this is z. These are the sort of values in your field. So you probably want to say something about, okay, if you go from here to here, you should see a difference of, you know, z minus x, which should be the same thing as going from here to here, and then going here to here, right? If these are edges on your graph, I mean, assuming these vertices are connected by the graph, right? So if you just consider the finite difference, the only data you have is the actual numbers on the vertices. This is trivially true, right? Because you're just saying, you know, z minus x is the same as y minus x plus z minus y, right? It's a very trivial statement. So again, no information on how to put numbers on the vertices. But if you suddenly had something, you know, assigned to these things, like you had an A here, you had a B here, and you had some C here, right? Assigned to those, you could demand something like, you know, B needs to be the average of Z and Y, or something like that, right? So only those functions that assign the average between two middle points are continuous, right? In this context, or some condition. I don't know if the average. I'm just saying whatever. Some condition that depends on Z and Y.
I mean, like I mean, on Rn, if you just plot, like, let's say you take a smooth function, right?
Yeah.
And then you just put 3 points, and then you draw edges between them. Like, there is no algebraic condition that you can come up with that the function values on those 3 points are satisfied, because a smooth function, as I said before, can be anything, right? Like it can go up and down, it can oscillate, it can do weird stuff. So that's why I said that we can assign each edge with like a power series.
No, wait. But no, that's not true. It's not that a continuous function cannot do anything, right?
Right, but like these, like x and y, like they're not the distances between them. Like it's a finite distance, right? It's not the distance is not like infinitesimally small that it should vary very like slowly as
Yeah.
epsilon
Oh,
goes
I
to
see. I see
zero.
what you mean. So sorry, I think I misheard. So you mean that you can assign x, y, z in any arbitrary way, right? There's no constraint.
Yeah, you can give them
Exactly.
any value.
That's my point. That was exactly my point. That you can. And what I'm suggesting is that if we allow something like, if we consider something like mapping numbers, mapping scalars to edges, then there suddenly are constraints, because suddenly you can use the graphic data precisely to constrain values, right? So
Oh yes, I see. Yeah,
you see what I mean?
yeah. No, yeah. I mean, yeah, definitely. I mean, there should be constraints, like 100%. Like, I did like even preliminary calculations. If you just consider like a normal graph, and then you calculate all the possible set of functions you can have, which is like a very easy combinatorial argument. And then if you calculate the set of all vector fields, like they don't match, because there is no restriction on the set of functions you can have. And so there is supposed to be, there are supposed to be restrictions. And essentially the point is that if I have like a collection of dots on the real number line, and if I grow that out to infinity by, let's say, and the rewriting rule can be very simple, right? To get that to like real numbers, take an edge and you just subdivide it. You just insert another dot, and you keep on doing that, and the dots get closer together. And so if you want that to resemble, let's say, a real number line or a continuous space, the function space that you define originally, and like, let's say you define a function space f epsilon, for every like subdivision you make. And as epsilon goes to 0, f epsilon should go to like the sort of smooth functions. F epsilon should have restrictions. If you just say f epsilon is just any function, like any scalar value at each point, it's not going to work.
Yeah. Yeah. So this, in fact, just in case Jonathan catches up with this live stream later on, as he has told me that he does sometimes, this might be related to one of his comments on having weighted directed graphs to represent things like torsion or dependence on path and so on. I think this could be sort of a natural sort of entry point of that concept. I was very unclear what a weighted structure would represent in the geometry analogy, but to me, having a graphic structure that is more or less static, right? That you have whatever it is, some collection of edges, hyper edges in general, and then that's your geometry, so to speak, right? And then you throw a possible function, possible field. Let's just think of scalar functions for simplicity, right? On that graphic structure, it makes sense to me that if, you just make a random assignment of scalar values to all the edges, including the vertices as one edges, right? Then you're going to get something that does not, in general, match with the geometry. Just like in a continuous manifold, if you take your set of points and just consider a set function valued on the real numbers or whatever, that's not necessarily continuous, or that's not necessarily smooth, right? You need to say, well, no, actually look at how the points in that space are connected, how they are in a topology, how do you have an open ball, blah, 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 all that story, to define what continuity means, right? To me, the analog here is to actually use valuations over edges so that you can constrain with the geometry of the space. By the geometry, I mean the graphic structure of the hypergraph, right? So to me, that's a very strong motivation. I have no idea where I'm going with this. Like I'm just saying this just because it makes a lot of sense mathematically at this point. Because really, I think it's a bit uncomfortable, the fact that functions don't know about your graphic structure ever in our current definition, but absolutely vector fields do, and everything else does, right? Everything else is dependent on the graphic structure. I think that is very uncomfortable. I don't think that's right. I think we might be, the things that we have worked out so far might be kind of degenerate examples of what happens when all the edge assignments are 1 or something, or 0 or something like that, right? And so we are looking at a subclass of functions that are, that behave sort of nicely in this sense, because they do form this weighted derivation algebra and all that stuff, right? But then, yeah, I think when you more philosophically, right, if you're thinking about what this graphic structure should represent, right? If you think that your space is discrete, and you're in point X or point Y, right? It kind of makes sense, okay, your space is discrete, sure, but if there is a notion of going from X to Y, right? That means that there exists some kind of data in between X and Y, right? Like there's some entity of betweenness X and Y, right? So the edge, the directed edge or undirected edge between X and Y is kind of populating that sort of virtual space between X and Y. So I would say, in the following sense, in the sense that you can have either edge between X and Y or no edge between X and Y, right? So that distinction of, having an edge or not having an edge, to me, because we are trying to model spaces, to me, that is like saying there's space between these 2 points, or there's no space between these 2 points, right? Because, if you can reach 2 points, it means that there's space between them, right? So
I agree. Yeah, edges must be assigned some value, some metadata.
Yeah, and then I don't know. I think it makes it more parsimonious in a way, because as I said, if you're really thinking that the data of the manifold is not the set of points, the data of the manifold is the points with the connectivity structure, which in the continuous case is the topology, the smooth case is the smooth atlas, blah blah, all that story. Then we need to do the same here, right? So the data of the hypergraph is not the vertices. The data of the hypergraph is the vertices and the edges, and therefore any kind of smeared structure like a function should be some kind of assignment to edges as well. I mean, this obviously complicates the picture, and we might want to, I don't know, sit on it for a little bit to see where this takes us. But there's yeah, there is a there is some degree of how to say, there's flexibility now to have definitions depending on how you assign um, the values here. Okay, sorry, I got a pop-up window.
I mean, they don't necessarily have to be values. Like they can be any. I mean, I'm assuming by values you mean elements of some set, or like, do you mean like real numbers or field values, or what values are these?
I would rather like remove any kind of reference to values at all, if possible. It's like if you can define everything with just a structure, it's like a multiplicity of edges, right? Don't weight your vertices at all. You already can assign a weight to it with just unary edges on top of it, right?
Yeah.
If you can assign, and you can just increase the amount of edges in all possible ways. Maybe there's like arbitrary weight can be, or arbitrary field can be represented by just layering just more edges in that on top of those vertices.
That's actually interesting. That's actually interesting. That's an interesting perspective. That's a very discrete finitary sort of like very disciplined graphic perspective. To really get rid of algebra entirely, you never use numbers, right? So yeah, that's actually interesting. So I'm gonna make a note here. So, oops, why is it so laggy?
Or even symmetries, right? You can also incorporate symmetries in your definitions of numbers.
What do you mean?
No, an edge symmetry, right? For example, can be not just a direct edge, because we consider in arbitrary edges also hyperedges.
Sure.
So they can have like arbitrary permutation assigned to them, for example.
Yeah. No, that's interesting. The only problem I see with that is I mean, I can't see how. I mean, I see clearly that you have a correspondence, say, z integer valued functions or natural valued functions on a set of vertices,
Yeah.
or on a hypergraph or a complete hypergraph. That's the same as multi hypergraphs, right? Like you can populate some complete hypergraph on a set of vertices, and then the counts of each kind of edge is going to give you the weight for that edge, right?
Yeah.
And then you can do just a hypergraph union, right? This additive union operation, and then you have
Like an addition.
Addition.
Yeah.
I wonder what it means to. I guess point-wise multiplication is just doing that, but I mean, we're keeping track of the counts of the multiplicity. but that in a way doesn't really fix. So I like your suggestion a lot, Nick, but in a way it doesn't fix what we're trying to do. In the sense that.
Well, what are we trying to do? Let's define that then.
Okay, sure, yeah. So, yeah. So, right. So one thing to do would be to know exactly. Okay, so we would like to have an algebra, an algebraic description of the hypergraphs, or sorry, of the objects that we call functions and the objects that we call vector fields that fits into a framework that is sort of analogous or is within the same description as conventional manifolds. And I think we pretty much got there with these weighted derivations and so on. But I mean, you're right. I mean, we should refocus a little bit what we're trying to do. So what we're trying, I think, I mean, my goal with this is that there should be, okay, the goal eventually is to have a way to bring back the concept of a manifold and to be able to have a formal treatment of these objects, which are defined from hypergraphs. Squint your eyes and you're basically, oh, that's just like a smooth manifold, right? So it makes sense to take a formal limit or something like that, and that can be made precise. More concretely, I think the main problem that we have now, what we're trying to solve, quote unquote, is that fields fields seem to just be assignments of of values to vertices, or in your language, it would be just considering multi-one edges, right? But those are completely arbitrary assignments. There's no way. I mean, the graphic structure, which is the connectivity structure, doesn't inform in any way what those assignments can be, right? So that's the problem. So in your language, the problem that we were trying to solve here in your language would be given a base hypergraph, right, which is some kind of pristine, simple hypergraph, right, that you're going to populate on top with multi-edges, as you said. That hypergraph somehow needs to inform what are the valid assignments of things, right? And I mean, it does inform it by saying they have to be subsets of this hypergraph in some sense, or sub-multisets in some sense, but
well, for example, maybe we can try something like a little bit different perspective of it. For example, if you think of the hypergraphs, maybe you should think of the points in your manifold as edges as points, not vertices. How about that? So basically, you maybe treat, and you can treat each edge basically as some kind of neighborhood of a point, right? So basically, each edge gonna define a neighborhood and a point around this neighborhood, around this point.
Yeah, sure, yeah. I think that's where this description that I was suggesting was going as well, right? Because effectively, I was saying you can go from x to y. It means that there's space between x and y, and so there's effectively like a point between x and y. But instead of calling it a point, you're calling it an edge, and so you can have because the arity of that relation of betweenness is arbitrary in order, right? Like you can say there is a space between x and y, but if you put z, there's also a space between them. There's a ternary edge there. There's between the three there is something, right?
Yeah.
So
because I kind of find more natural, like I'm thinking of edges as points. So especially when you think about like causal graphs and space times as the computational evolution.
Right. No, but
edges are more naturally
sense.
representing points in space.
That makes a lot of sense. I mean, I think that's exactly my suggestion. What I'm trying to say is that my suggestion to consider the edges as part of the places where functions take values, right? Which is the topic of conversation right now, but we can think of other concepts. I think that's effectively what that is doing. Now, of course, I guess, yeah, it's almost like, if you imagine, it's almost like this discrete model of space is almost like, because I know that you say you like to think of the edges as points, but at the same time, if the concept of a path should be a sequence of directed edges, right? I think it's difficult.
Well, you can define it, but basically vertices of the hypergraph would act as connections between those, right? Because now they define what edges are connected to each one.
Yeah, but
So
isn't it a bit strange? Isn't it a bit strange that you have different kinds of points? What does the order of a point mean? What does the order of an edge, if the edge is a point, what is that order encapsulating? What is that information?
I'm not sure what order would encapsulate. For now, we can just think of it as all of those as unordered edges, right? So just as an ordered hypergraph, each unordered edge is.
No. I don't mean the order. I mean the arity. I mean the.
Oh, okay. The arity.
I don't use.
No, the arity somehow should represent that constraint that you seek, right?
But that's why. But that's why I'm thinking that, if you really want to push for edges as points, then that's to say that your concept of point needs some kind of extra integer that comes with it, which is this arity, right? And that's what I don't see. I don't see that. I can clearly see that if I have, I can see edges as betweenness information, right?
In your manifold, I guess you can compute a bunch of things about the point, right? So there's some I don't know. There's some
without the neighborhood you can't, right? That's the problem. That's the problem.
Well, the edges define the neighborhood, right?
Okay, well, that's right.
So
okay,
you given this manifold,
yeah.
So you can compute something about the point around the point.
Okay.
Using the edges.
So, okay, but that's that.
On curvature, maybe, No,
sure. No, I understand. Yeah. I mean, I'm not opposed to any, I don't have any dogmatic preference for any particular choice. I'm just wondering how you recover stuff. So when vertices are points conceptually, then sequences or chains of directed edges are paths, and that gives you the very immediate notion of direction and what will be derivative and all those kinds of things, right? It sort of takes you by the hand very quickly to interesting things that you can define and make operational very quickly. But if I consider that my data
you can always take duals, right? You can just take a hypergraph dual. Now you think of the vertices as points in that dual hypergraph representation.
Sure, but the problem is, taking the dual doesn't solve anything, right? Because it depended on the choice you made. If the choice we're not agreeing on whether the choice is capturing what we want, the dual is going to capture some dual construction of that choice. So it's you can always take the dual, right? Like there's no, it doesn't.
Yeah, but then what is your problem then again? With
the issue I'm having is that how you, in particular with paths, right? If I don't have, if you say that edges are literally points with a neighborhood around them, right? And that's how I should be thinking geometrically. Then then paths should be sequences of edges, right?
Yes.
And which is okay, that's not a problem. But you could have a path that goes from, I don't know, like a ternary edge to a quaternary edge.
Sure.
If that makes sense. Yeah, I don't know.
Well,
I mean, maybe
I don't have any.
maybe that makes sense. I mean, I'm as I said, I'm open. I was not seeing how the path structure was immediate and intuitive, right? But it might be that it's less intuitive and it's more, it makes more sense. I mean, I'm actually slowly warming up to the idea that actually that could make sense, right? Or rather, what I'm warming up to is what I said earlier, which is that we might want to consider. Okay, this I really liked your comments because you pushed me into this position. I think it's a good position. We might want to take seriously that we have a hypergraph, right? So all hyperedges are equal in worth, right? There's no dictatorship of the vertices over the edges or the other way around, right? So all edges, right? And vertices are one edges, right? For now, I'm not gonna make a distinction. All edges are places of your manifold. Right.
Actually, I want to still distinguish between vertices and edges, because for me vertices are like connections or links between the edges, right? The edges has like
but in geometry, what is
that you actually rewrite.
So what is in geometry? What is a link between points? It's a set of points, right?
Well, that's what we want to determine. That's what we're trying to build, right? It's unclear for now, but maybe that's the intuition.
What I'm trying to say is that in geometry, in classic geometry, whatever.
Well, there's some kind of map, right? You define two neighborhoods and you kind of impose that there should be, when they intersect, there should be a map, right? So that you can. So in a way, the vertices of a hypergraph act as this gluing condition between two neighborhoods.
Yeah. What I mean is that gluing condition is made of points. I mean, the atlas structure that's to do with the specific topology of how the things are distributed, right? But in terms of having a set of things, which is the points, the only thing that is between points is more points, right? Like it's not that there's like different kinds of things, right? So that's what I'm suggesting that your idea, I think, is perfectly good, because it might be that we want to think of hyperedges in general as places, right, in your manifold, and the places have a relational structure, right? Like places are relational, so you can say, if I am at X or I am at Y, those are two different things. So those are two different one edge place statements, right? But you can also say I am between X and Y, right? Because that space exists in my hypergraph. Therefore, you say I am on the edge XY, right? So similarly, you can say I am between X, Y, and Z.
Maybe you don't have to impose that there is an edge. You just can say that those edges basically share the common vertex, incident to each other.
No, but there was no two edges. I was just making a statement about one edge, right? So, I mean, I think there's two things going on in our conversation. I think you're thinking more of a dual perspective from what I'm thinking, and there's something of that going on, that you're thinking more of vertices as the point of connection, sort of the relational data being the vertex instead of the edge. I think there's a bit of that going on. There's a bit of that going on, but I don't think that's just conventional in some sense, right? But what I'm saying is something beyond that kind of more conventional choice between you and I, which is that we should consider all the hypergraphic data as locus data in some sense, right? Like, as I said, all hypergraphic data is place data, and so you can say things about, it is a meaningful. Let me put it this way: it is a meaningful, in this triangle XYZ, it's a meaningful geometric statement to say I am, if that's all 3 points in space. Let's think in terms of sort of Euclidean geometry, some basic affine geometry or something, right? There's basically a set of statements that you can make, right? Which is to say, you are in X, Y, or Z, because those are singled out and you can see them. You can say that you are between X, Y, and Z, right? Like there's in some region between them, that you are bounded by them in some sense, and you can make that same claim for any subsets. So you can say that by X and Y, you're between X and Y, So the data that you would have in practice would be a specific set of graphic structures here. So you would have like maybe X, Y, Y Z as edges, and you would have like maybe the X, Y, Z hyperedge, right? So in that particular space, there's no X and Z don't have a place between them, right? Like they are distant. They are not, they don't have an in-between space between them. But there is an in-between space.
That's the nature of discreteness, I guess. It's like, should it be? No, should it always be the in-betweenness?
No. What I'm trying to say is that the different hypergraphs represent different topologies, right?
Yep.
So by looking at the hypergraph, and maybe, I don't know, will this blow up again? Let me just try it again. Maybe it now behaves. But if I try to do something like this, okay, it seems to work better, right? In this particular space, let me say it like this, right? In this space, I can, I can be in 1, 2, or 3. I can be between 1 and 2. I can be between 2 or 3. I can be between 1, 2, and 3, but I cannot be between 1 and 3, right? Like there's no place between 1 and 3, right?
Yep.
So this space is different from this space, which is different from, just having just this space where you can only be between them, but no, right? But
yep.
our hypergraph rendering already kind of communicates that, right? Because it draws a straight line between them, so it's the shortest,
So, well, all I'm saying is just it's more natural to me to think of, as you say, edges as places. So,
edges as
so
places,
this is a single edge, a single point.
Sure, I would say, yeah. I mean, I think that's more like a philosophical debate whether we should think of an edge as a thing. I think that we can definitely agree on we're on the same page that edges should be places in general, right?
Okay. Yep.
Okay, that's a lot of progress. That's actually, I'm gonna make a note of this thing here. This might actually solve many of our problems. Just this little 3-word phrase. I wonder, because I totally see your point. I understand that you're taking this more dual perspective, that vertices, you want them distinct because they are the connectivity conditions on neighborhoods. I totally see that. I can understand that.
Yep.
And
it's even more clear as soon as you start considering rewriting of those places.
The rewrite.
By going, yeah, because you rewrite edges, not vertices.
Correct. Yeah. Well, you can rewrite vertices, right?
In a way, but yeah, they kind of then gonna affect all the edges that it connects to in a way. So it's basically you're writing edges anyway. That all the edges that connect to a vertex are affected.
Well, that's there's some Pandora's box there to go down, but so maybe let's discuss that briefly. But let me just address some of the comments here in YouTube. So there was some comment about defining addition on on tangent spaces. Yes, basically now the multiplicity allows you to do that. Then Dugan Hammock was asking, my opinion, hyperedges could be used for defining neighborhoods and as a basis for defining discrete topology for discrete manifold. Yes, I think that's where we've converged here. Now, interestingly, there is literature on hypergraph paths, meaning sequences of edges or hyperedges. And so I don't know, should we do this live? Should I? Okay, so we have a forking point here. I would say we can go for maybe another half an hour or something, depending how you feel. You can let me know when it's been enough. But I have time. I can go for a while.
So there's this comment from Martin about geometric algebra and their definition of points. I kind of know a little bit about it. There's like this conformal geometry on all those different, in all those kind of spaces.
Oh yeah, sorry, then
Basically,
scroll down. Yes.
so that you can,
Yeah.
so that you can define points as vectors in this algebra, and all different geometric objects as just other kind of, in general, multivectors, right?
Oh, for
So that
sure.
you
Yeah,
can
no, this is
define
very similar.
point,
Yeah, this is very analog.
line,
Yeah.
plane, yeah.
Point is a
So
vector which
basically,
goes to zero.
if the multivector is our hyperedges, if you're gonna make this geometric algebra connection, if our hyperedges are multivectors, then what would be, well, then squaring, well, it depends what kind of algebra you're doing.
Well, I mean,
In a way, yeah.
yeah. I mean, geometric algebra. Okay, so geometric algebra is specific for metric spaces, and we are not necessarily thinking of metric spaces here. It might be that we are overlapping with metric spaces by the nature of discrete spaces. That might be that any graph is already a metric space just by the information that the combinatorial data.
It's just maybe there's like a natural choice of basis that has similar algebraic properties as in geometric algebra, so that there's some multiple things that square to 1 or to minus 1. What
I
would be
mean,
the geometric?
Yeah, so I am aware, like I know the basics of. I mean, I know what this geometric algebra is about, and the Clifford algebra and so on. And so the geometric analog of multivectors, these are, you have points, vectors, multivectors, all these things, right? Like, so it's basically the exterior algebra of your vector space, right? So in that exterior algebra, these multivectors in general, they are very natural geometric structures because they are essentially oriented shapes, oriented flat shapes.
It's like hyperedges. Basically, it's like almost one-to-one. You can think of the one vector as a unary edge. A scalar in that sense would be a vertex, right?
So I would not rush to mapping hyperedges to that because they are oriented, right? So if you tell me you're considering oriented hyperedges or hyperedges with some very specific symmetry property, then I might be much more willing to make the connection. But if you're thinking of something like undirected edges, my opinion is that those represent much more closely space, the intrinsic space, which is not what geometric algebra is about. Geometric algebra is about the metric space of the tangent structure on that space, right? So, which of course is tightly connected, but it's technically not exactly the same, right? And just not to muddle the connections here, I would keep that if we're thinking of hyperedges generically, undirected in principle, right? Like then I would say that we are still firmly in the realm.
We're still seeking for some property that can define these constraints of functions, and one of the possibilities is the symmetry. Yes, maybe the most natural choice of symmetry is the one that behaves exactly as geometric algebra, for example. So that as soon as you like do this wedge product between your vertices to make your hypergraph with some symmetry, right? Maybe it behaves very analogously as vectors, so that they anti-commute and have the same kind of
anti-commutation. I mean, this anti-commutation is built in some sense, right? It's So that's what I mean. That if you're thinking of undirected hypergraphs, right? We are in this class of undirected hypergraphs, right? There is no real way to think of orientation or to think of ordering, right? Like it's kind of forbidden. I mean, you can always declare it by your godly powers that okay, this is a tuple and I'm gonna say this is 1, this is 2, and this is an order that I established. But the fact that they are undirected edges means that you only have sets or multi-sets of bags. Canonically, there's no structure to pull from, right? So any choices will be some kind of some gauge fixing that is completely strenuous, right? So and so I don't know. I'm not saying there's no connection, because we are obviously going to make the connection if this works, right? Because that's the goal, that we want the geometry in this discrete sense. But I'm trying to keep things as tidy as possible, and I think that geometric algebra has to do with simplicial hypergraphs. Like, you need something that looks simplicial in the following sense, right? In geometric algebra, if I give you an oriented plane, right, or actually it's an oriented area, right, that area has a boundary, right? Because by definition, that's what it means, right? So that boundary is oriented as well. It has an induced orientation, right? And so those are vectors, bivectors, one vectors, all these kinds of things. They has this nested structure, which is precisely simplicial, right? This is exactly what simplicial hypergraphs do. I mean, simplicial complexes, right? Again, there's nothing new, right? Like, I mean, algebraic differential topology computing with simplicial complexes is fairly established, right? Like, I mean, it's nothing super surprising that you can build your triangulations, your discrete models of your manifolds. You actually compute your cohomology on that discrete space, and then you come back to your continuous space, and you have the actual cohomology, right? Like, that's something I used to do as an exercise when I was doing my degree, right? So that's what I think is more closely happening there, right? Like, when you have this this simplicial like structures, you're going to have very closely related like structure, like or patterns, like the geometry in geometric algebra and things like that. But if we pull back from that possibility and we just say we want to be as analogous as possible to something like open sets on a space, right? Because that's kind of the level we are at. We are not yet developing what happens when you have open sets, but also metric, and you consider the tangent structure of it, and you have this notion of a vector field and so on, and then you develop this geometric algebra machinery. But we are kind of in a more primitive state where we are just looking at undirected edges on vertices to model possibly topological spaces or something analogous to it. So I would say that our realm is just consider generic undirected hypergraphs and try to come up with a good definition of a continuous function on this thing, right? And I think it was very important that we realized this edges as places, because in a way it was kind of knocking on the door when we started to think about, well, we might need numbers between the vertices, and we might want to put them on the edges. And like, I think that was just sort of like this fact, edges as places, knocking on the door, right? So it's perhaps natural that we end up considering.
I have a question.
Yeah, right.
When you say place, like, do you mean like I mean, so I don't know any topos theory, but I do know that topos theory is like topos means like place or like something like that, right?
Yeah.
So over here by place, do you mean like the space in between, or like do you mean a play or like a thing where you can do like a rewriting rule or something like that?
Well, yeah. Well, let's clarify.
Literally just a manifold point, right?
Yeah.
Just.
I mean, I want to say something more than a manifold point, because it might, otherwise I would put point and just be contempt. I mean, point is a word that you use happily in this context, right? When I say place, is more of it's kind of a philosophical point. It's kind of a more conceptual point. It's not a technical term. I mean, topos is the Greek root for place, right? And that's where topology comes from, and so on. I mean, topos theory, the word topos in the technical categories theory sense is very, very removed from the etymological origin of topos as a place. So don't think that there's a connection there to. I mean, topos theory is just some very special kind of category theory.
Okay.
So
on the website of the Topos Institute, I think the first phrase they use is topos means place. I'm like, okay, this is about geometry, but clearly I was mistaken.
No, I
about
mean,
logic, I think.
originally
Right.
it comes from that, right? Like,
okay.
I mean, the category of topological spaces is a topos. Right? So
Okay.
so anyway, but yeah, like edges as places is meant to elicit an idea, right? So when you think of a space, there are many ways to let's just make a very broad mathematical remark, maybe also for the audience might be useful. When you think of a space, in mathematics. I mean, the word space in mathematics is used everywhere, right? Like it's thrown around a lot. Oftentimes, it's used when it's not really legitimate to use it, but very often it is very legitimate to use it, right? So when you have a set and someone, typically not a mathematician or not a pure mathematician, very often these people would say, oh, I have a space of such things, because they just have a set to choose from. And then people like to have a mental picture that there's like a space of things and they can pick from, and like the room is floating in the room and they call it a space, right? But that's just purely a kind of a conceptual term. Normally mathematicians call spaces something that there is a set that has a specific extra structure that allows you to specify something about nearness or direction or betweenness or etc. Right? And so all those notions are words that are fairly vague, that are not meant to signify a particular definition, mathematical definition, super rigorous, because at the end of the day, what mathematics is, you know, we have intuitions and we try to capture them rigorously, right? That's all we're doing. So in the notion of space, you can go different routes. So just for people to have a reference in the audience, to have a reference of where you could go. For example, an affine space, right? Something that is mathematically the closest to your day-to-day life in reality, right? Like you walk around. There are many ways in which you can codify that. You can say, well, you have a set with no structure, but then you assume that there's at every point you have a way of assigning vectors that basically point to other points, and there's a bijection at least locally, blah, 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 blah. That's a particular mathematical structure that has, you know, a set with a binary operation that and a map that and so on. Similarly, you could just say, well, actually, I'm going to take a space of numbers that has nothing to do with reality. There's some construction of rationals or some construction of, you know, whatever, and I'm going to make this definition of coordinate chart, and I'm going to say, you know, whenever you have collections of such numbers that transform in this way, they are going to represent the similar thing, and obviously that's a theorem. You prove that those things are equivalent, they are isomorphic, and there you go, right? Similarly, you can purely algebraically encode an affine space with a ternary operation that is called a truss, and you can actually, it's some kind of analog of a group that is ternary, and it's entirely algebraic. You know, everything is sort of swept under the rug, and you only see a ternary operation. So these are all very mathematically different objects, but they are all encapsulating what we call a space, and that's why they are all called affine spaces. And you say these are all different instantiations of an affine space, right? So when I say edges as places here, I am trying to do an analogous thing, right? I'm trying to say, forget about your traditional set theory, forget about your traditional mathematics, your traditional algebra, and so on. Think more computationally, think more in terms of what, you know, Nick and I are more fluent on, which is hypergraphs, discrete data structures, rewriting, blah, blah, blah. Think more in these computational terms. And let's try and encode a notion of place in this context. And, you know, this has been the adventure of infrageometry since, you know, we started thinking about it. And today, the claim of edges as places is that we were, at least I was, thinking of vertices as places for sure. And Nick then said, well, to me, vertices are more like overlaps and more like connectivity between neighborhoods. And I was like, okay, sure, but, you know, and I tried to sort of work to some kind of middle ground, pun intended, I guess, in this context. And then we realized that actually, and then we had this problem. You had the problem, right, Uti, for what is a continuous function in this discrete setting? You know, things are arbitrary. We don't have constraints. Blah blah blah. It seems that if we had some kind of values in between, that's kind of a constraint, and so on. So these are sort of confluent ideas that take us to this concept of we should think that edges, which is something that happens between vertices, right? Those are also places that can be sort of quote unquote geometrically inhabited, right? So that's what what a place means. And more technically, a place is anywhere that path can take you. So the space of paths has grown now from the usual space of paths of a set, which is basically the set of words of set of the element symbols, right? And it has been upgraded to a set of words of edges. You know, it's a bit more sophisticated, right? It's a bit larger. So so yeah, that's the sense in which we want to take this a bit more seriously, and I really wonder what the immediate implications are. I don't know. Some of you had some immediate thoughts that wanted to run collectively here, or would you like me to maybe say something about the rewriting perspective and see if this actually informs that perspective? Because I have no, I mean, before this meeting, I was not thinking of edges as places, and now I am. So,
Oh, another way of thinking about it, as I like it, basically think of vertices as some kind of, in computational terms, you can also think of them some kind of links and maybe even memory addresses
sure.
where the things live. And for the rewriting procedures, it's very useful because I have a slightly more useful generalization of hypergraph definitions when you have links, right? I call them just link hypergraphs. When you just basically any hypergraph, but you also invent this auxiliary vertex at each edge, right? And you just think, if you think of those vertices as some kind of addresses, those basically define where your edges live, right? It's like some kind of memory, address where the edges live, and all the other vertices are basically pointers to other edges. So you can just walk around and basically compute with it. So it's more natural computational object.
Sure,
When you just
yeah,
think
yeah.
the vertices as pointers to other edges, and you just point to things and rewrite those.
Sure. Yeah, absolutely. And that also opens up, I guess, the door to hypergraphs, right? Which is the when you take your set of edges and you think of hypergraph structure on that set, right? That's a sort of a higher order hypergraph in some sense. But those, I mean, hypergraphs. I mean, it sounds like a meme, but like they are not. I mean, if you learn something from higher category theory, is that when you go from one category to two categories, you basically learn everything there is to learn about going higher, right? So I think when you look at hypergraphs and you think of your edges as kind of some static thing that you want to do things with, this perspective that you're talking about, Nick, I think is quite close to the idea that edges themselves are going to be thought of as some kind of just vertices everywhere, right? Like they have some assignment of vertices, and then some kind of graphic structure on that is going to be information about how you rewrite them or how you compose them, how you delete, add, and so on, right?
Yeah, it's some kind of.
What about
it's
this?
Kind of
What
analogy to
about
Minecraft.
Sorry, say that again, Nick. Sorry, Udi.
It's like, well, Uchi, go ahead.
No, but
it's fine. I was just saying that it's like the more smooth you get, the more easier it is to interchange between points and edges. Like that's one way you can think about like smoothness in this context. Because the more smooth you get, the more like I don't know, the more clear the bijection between like edges and because over here, if I have just three vertices and edges between them, we know that ultimately we should like the edge will contain points. So the edge is really nothing but just like a bunch of points. And so there the distinction between edges and points becomes like less and less, and you can take the dual and the dual will be the same essentially.
Oh yeah, that may be useful. Yeah. So basically you can define your smooth manifold, discrete manifold as the hypergraph that is dual to itself. In that
I wouldn't go that far, but like something like
wait. So what is the statement here? So
I was Nick, you can go ahead.
oh, it's a smooth discrete version of the manifold is a hypergraph that is dual to itself. By dual means it's like this line graph generalization to hypergraphs, right? By line graph is just like a function in the Wolfman language. It just turns every edge into a vertex and connects them with the incident. If two edges are incident, then you have like an edge in its line graph. So this generalization to the hypergraph.
Yeah.
When this incidences also makes some kind of new hypergraph, new hyperedge. If you're gonna get the same hypergraph again by this operation.
But why should that be smooth?
I don't know. That's Uchi's intuition. I don't know, but
I
I'm
mean,
just.
I mean, do
No,
you
no,
have an
I'm not
intuition
saying
for
that
it,
should be
or
smooth.
I
I'm
mean,
not saying that should be smooth. I'm saying that in the limit, it's smooth. Like I'm saying that in the limit, like you can interchange between edges and points, and the dual is like isomorphic to the original one, like in the limit. Because in the limit, if you have a smooth manifold, then if you draw an edge or like a path, right, and then you populate the path with like points, then it's like the path is like useless to think about because it's just like a bunch of points. So it's like the dual is the same as the original one. But like then Nick claimed that like a discrete smooth hypergraph is one that the dual is the same.
no, okay, so what I think, I mean, I don't know. Maybe that's further down the line we realize that there's something there, a connection between self duality and smoothness in the analog or something. But I believe that smoothness is going to be connected to some properties of the hypergraphs that are invariant under some kind of transformations, right? So if you think about it, your hypergraph, it is very likely that you're going to have different. I mean, let's run it the usual case, right? Imagine a smooth space, and you're interested in some topological data and some homological data, some things like that. It is perfectly fine to take triangulations of that space and compute with the triangulations, and you're going to find the right numbers, right? If you compute the Betti numbers or you compute whatever, right? Some compactness properties, connectivity properties, all those kinds of things. But, any triangulation of that space is going to compute them correctly, right? So at the end of the day, a manifold is really a collection of representations and a set of requirements that you want that those representations tell you about, right? So in that sense, if we are similarly honest with our hypergraph picture, a discrete space, a discrete manifold, is going to be really some class of hypergraphs. It's not going to be one. It's going to be a class of hypergraphs that all share some kind of properties, right? And there's a well-defined notion of what it means to be equivalent in this sense, right? Which obviously is going to be hypergraphic. I mean, hypergraph isomorphism is going to be an equivalence, but not all equivalences are going to be hypergraph isomorphism, obviously, right? So and many of them are probably going to be formulated in terms of rewriting, right? They're going to say, well, after you do a all pass rewrite of these particular rules, they become this. Then they are equivalent under such and such, right? Whatever it is that we think of in this particular context. I think that's what something like smoothness is going to look like, because it sounds like a philosophical question, but if you ask, what is a sphere, or what is S1, what is the manifold, what is that, mathematically, it's not obvious what the answer should be, right? I mean, obviously modern mathematicians will tell you, well, is this particular object in the category of smooth manifolds that has this relational properties to all the other manifolds. Sure, that's a categorical relational description of the object, but if I tell you, well, take R2 and take radius 1, that's an S1, but there's also radius 2, there's an S1, etc., right? So there's an infinite collections of representations of S1 that they're all kind of S1, they preserve the S1-ness of it, right? So that's what I think differential geometry is about. These are statements about invariance of representation, which obviously is connected to charts and coordinate patches and how you can change arbitrary coordinates. That's obviously sort of the sort of atomic version of that sort of generality that you have invariant notions. So anyway, I'm just saying this because we will have
Maybe
to
we should like, sorry,
yeah. Go on. Sorry, go on.
I was saying maybe like, I mean, maybe the way we should formalize, what a function is or like what a chart is in the discrete setting or what smooth is, should be that the invariance is like clear, like it's obvious. Like in differential geometry, it's not always like it's the chart thing. Like we want the transition functions to be smooth and stuff like that, so that things are invariant, and that's why the dimension like the dimension of a manifold is always the same. If you demand like the gluing condition is satisfied and so on.
Yeah.
In the discrete geometry setting, like these things should like be more evident in a sense, like the invariance.
Oh, right. Well, yeah. I don't know if evident or at least explicit in some sense, because they are going to be finite, right? They're going to be
Yes.
finitary constructions because they're going to apply to finite hypergraphs, and so they are going to be algorithms that, or they can be expressed in terms of algorithms that apply on finite things. Perhaps this is a good segue into the. I don't know if you had something to say, Nick.
Rewriting.
Were you waiting to say something? Sorry, I maybe I misread.
Are you asking me or Nick? Or...
Nick. I don't know if Nick was waiting to say something.
No.
Oh, sorry. I just misread maybe the motion of the camera or something.
I'm excited to see like the rewriting stuff.
Yeah. So this actually might be a good segue into the rewriting stuff because, I mean, don't expect much because it's just a sketch of an idea, but I think there is potential here. So, okay, let me motivate. Let's forget about edges, are places for a bit. Let's just forget about that for a second, and let's go back to the old picture, which I guess, I mean, could be thought of as some kind of, you only think of binary edges, and I think it's fine. It's not wrong. It's just incomplete. Let's put it that way. But before I move on, let me address some of the comments. Some nice conversation going here. So yes, Dugan-Hammock space usually implies there's a set with a topology. That's usually the case. And Martin Stepanek is making nice connections between geometric algebra and hypergraph rewriting. So this should be worked out at some point for sure. Like there's going to be a very explicit correspondence, and we will work it out. And I'm going to comment on this in this rewriting section. And then Dugan-Hammock, I don't see advantage of going to the dual view. Just take a dual and then take the dual's vertices and places and treat the hyper edges as connection neighborhoods. Yeah, exactly. That's what I said earlier. That I think taking dual is just it's kind of an arbitrary choice to begin with, and whatever your interpretation is, you take the dual, and that interpretation is flipped, and so on. Okay, so what is the motivation? The motivation comes from the question that we had in the context of defining calculus on manifolds. So imagine that I guess we have a notion of vector field, at least in the old picture, of what a vector field is. And there's, the question of, okay, so vector fields correspond to finite difference operators. Finite difference operators, on the other hand, belong to the set of operators of functions, right? The set of such objects that send functions to functions linearly. And so the question is, okay, so those things can be added and those things can be composed. So it can be pointwise added and can be composed just by nature of maps, right? So the question is, what is the analog for the vector fields, right? If you think of not the transformation of functions, but of the geometric objects that we had in mind, so the assignment of directed edges to each vertex and so on. What is vector field composition and what is vector field addition, right? So some people might be raising their eyebrows in the audience, thinking, wait, but you can't generally compose vector fields in differential geometry. Yes, that's correct, and we can't generally compose vector fields here, as you would see. But anyway, let's see the motivation. The motivation is in this picture, right? When you have a vector field like that, it is unclear what it means to. So okay, so there's an obvious meaning for a composition, right? Because you can say a vector field is just a mapping of vertices, because that's what it is, right? By definition, there's only one vertex assigning to another vertex. It's not necessarily bijective or injective or anything like that. But you have an assignment. So if you have two vector fields x and y, you can just do first assignment and then do the other assignment, right? So in practice, what that is doing is sending, a vertex to map with X to another vertex, and then from that vertex you map with Y to another vertex. So the net result of that is, you keep track of the first vertex where you were standing, and you record the last vertex that you arrived, and so that's a new edge, right? That defines your directed edge in that order. So so the question that kind of prompted this was that the notion that these two compositions form a vector field effectively corresponds to the fact that those edges belong to the tangent bundle of your graph, right? Of your discrete manifold here, right? So in general, they are not. It is not defined in general, but in certain contexts, it might be that it just happens that these two things compose along the tangent bundle. If you had a complete graph, for example, then all the compositions of vector fields will be defined, right? Just to make the example of the case. So yes, so Dugan-Ham correctly points out that flows and manifolds can be composed, and vector fields can often give rise to flows. That's exactly the analogy. So that's what we mentioned last week, that you can think of these vector fields as sort of time one flows, right? Finite time flows. You can think of that, and obviously vector fields induce flows, and the flows can be composed. But obviously, when you compose the flows, you need to have finite flow parameter, right? And that might just create so it might create non maps, right? In that sense. But the flows themselves are perfectly well defined, and the composition of the flows is perfectly well defined, right? Because they are just maps from the manifold to itself, and you can just compose one after the other. So okay, so composition seems to be fairly well understood. Okay, fine, right? So vector fields are like vertex mappings. That's fine. But what about addition, right? What should be addition of vectors? And so addition of vectors, if you want to get a little bit philosophical about it, you ponder, okay, where does the addition of tangent vectors come from in a manifold? The immediate answer is it comes from the model space where you're taking your charts, right? Because if you model them on Rn, or you model them on some vector space or some affine space, some Euclidean space, that space has an additive structure by definition, and that's where it comes from. But you can be a little bit more sophisticated than that and say, okay, but what is the role of that additive structure in that model space? What is the additive structure in that model space? And in my opinion, what it is, it's the property that paths are infinitesimally composable, meaning that if you look at a point and you don't go far away, you can effectively flow with directions, right? A direction in your neighborhood is going to define a flow in that neighborhood, right? This is obviously not true for the globality of the space, right? In the entire space, that makes no sense. But locally, that always makes sense. If you choose a direction, you can flow with that direction, right? So you can define a local flow with that direction. So addition is effectively a composition of local flows, right? In the chart, because if you look at what addition does, you take your vectors, you represent local curves. What they are doing is you're basically saying you're flowing first with this curve, and then you're flowing with this other curve. And so those two curves are adding together the tangent vectors when they are composed one after the other, right? So okay, so that's kind of the context of where we are. Now, how do we spot this sort of structure in a discrete manifold, right? Because obviously there's nothing like what it means to be a local flow or something, that doesn't mean anything in our context. So what I would say is that what characterizes flow composition in the geometric setting is this rewrite rule, right? It's this kind of diagram. You have one point x to point 2, then y to point 3. So you compose together and you have x composed with y. Oh, Nick, by the way, if I try to rerun this, it should be labels.
The edge labels.
The edge labels are going to be much better. So good. That's amazing. So let me just quickly rerun this.
I have to say I have to leave soon, like in 2-3 minutes. But like, yeah, I'm just pointing that out in
Okay.
case there is something really important to discuss
No,
right
I
now.
think that this was the nature of today's stream. So should I wrap it up in how long you say you have? 5 minutes? 2 minutes?
I have to leave in like 2-3 minutes.
Okay.
But like
So
it's
maybe
fine if it
Nick and
goes
I
to 5
can
minutes.
stay for a bit and chat briefly about this, and then so I mean you can leave whenever you have to go, and we'll go on for a bit longer. Is that okay?
Sure, I'll chat with you like later probably.
Sure,
Or
sure. Yeah.
yeah.
Yeah, we'll continue the conversation. Well, thank you very much, Udi. Good to see you.
Yeah, thanks.
Right.
Thanks, Udi.
So oh, that's much nicer. That's much nicer. Such a simple change. So right. So my thought was, okay, if you have two vector fields, which could also be locally defined, so basically you pick a subgraph that has the property of a vector field, meaning only one edge per vertex kind of situation, then you can say, well, I'm going to define the composition vector field, which is the vector field that follows this rule. You know, you do a one-pass rewrite, this operation, right? And then you get a blue vector field, which is a new partially defined, whatever, local vector field, which if these were all totally defined and everything is in place, it corresponds to the actual flow composition vector field, right?
Yeah.
And then
so
yeah.
what it would do to the vector field at vertex number 2? Is it just basically undefined, right?
No. So
it depends, but
so this is what I'm saying. This is we have to drop the condition that these are totally defined. So that is completely thrown out of the window. I mean, to be honest, to just say that vector fields had to be, assignments to every, that's just a kind of a tradition from differential geometry, right? Like there's no need for that. Why? I mean, there's no problem that a vector field is partially defined, right? Like in principle, that's not, the fact that a vector field is globally defined is not what makes them vector fields, right? It's not their distinctive feature. The distinctive feature is how they behave locally as flows, but infinitesimally and so on, directional derivatives and so on. It's not about the fact that you have every single point of your manifold has a value for a vector. I mean, that's not going to be important for us because we're in finite conditions, right?
but I see it's just a rewriting rule. If there's some actually an edge at vertex 3, it's gonna make a new one at vertex 2. That
yeah,
right.
Exactly. So it's creating it's creating a new edge, right? So from the data of two vector fields, you do a one-pass rewrite, you have the data of a new vector field, right? And so you can ask things like, does that belong to the tangent bundle? Is it a subgraph of the tangent bundle graph? All those kinds of questions that we said before. So just reality check that rewriting makes sense in this context. I mean, it's just a very basic way of saying that you can just compose like you said, like matrix, the adjacency matrix multiplication kind of operation in this context, right?
Yeah.
So just as
Is
a
it
motivation,
confluent in general? Is it going to be confluent? Does the order of rewriting going to matter in that case?
absolutely. Oh, order of rewriting? No, shouldn't
Yeah.
be. No, because it's labeled. It's labeled rewriting.
What do you mean?
So you're rewriting x and y in that pattern, right? That's why I wanted to use colors.
Yeah.
So and the outcome of a rewrite has a label that is like Z, right? It's not, you can't rewrite it again. That cannot enter.
Okay.
Right? That's what I meant by one-pass rewrite. That's what I meant by one-pass rewrite. Right? There's no ambiguity. It's basically I mean, we know this, right? Is the matrix multiplication of.
You have to think that you're writing just the subgraph of your tangent bundle. You just want to have. I just was confused first.
Oh, sure. Yeah. So you are rewriting, exactly. You are rewriting, well,
yeah.
You're rewriting the pattern matching that has the labels that carry the vector fields, right? So the vector fields are labeled by their name, right? So I mean, you can think of, right? I mean, that's x12. That's the name of the edge, right? x12. So that x12 only matches with y23, and that makes Z13, right?
Yeah.
Or
Well, so labels are important. I'm just wondering whether you can do it without the labels, the same kind of
no, I don't think you
But
can.
what kind of subgraphs?
I don't think you can. No, I don't think you can. I mean, I don't know if there's some kind of workaround, but I don't know. But I mean, the point is, even if you can technically, you don't want to, because the labels are what have the meaning about geometry, right? This is what vector fields are, right? So we definitely want the labels as part of the data, because otherwise, I don't know what I'm talking about. If I can't really tell apart two labeled set of edges, I don't know what I'm talking about. Okay, so anyway, so this was just a reality check that this makes sense. Cool. Then I would suggest that one way, and this is just a proposal, I haven't thought too hard about this, but I would suggest that addition.
One more. Can I just one more comment?
Yeah, please. Yeah, go ahead.
Why do you like the right hand side drops the original vector fields?
I mean, that's just for cosmetics. I mean, that's just for cosmetics. Yeah. There's no deep meaning.
But for the actual rewriting rule, you still can preserve it.
Sure, yeah. I mean, I think this is the philosophy of labeled rewriting, is precisely that, because things are labeled, you always have the sort of the memory storage of where your things are, right? Like if you say X, it's highlighted, it's there. Maybe you rewrote it and it disappeared, but X is still part of your data, right? It's because it's not really just like how do you call this, like stock hypergraph, right? It's not just like you just have like a bunch of hypergraph, just move it around. It is like refined hypergraph. This is the X flavor of hypergraph, Y flavor of hypergraph, Y composed X flavor of hypergraph, right? And obviously, I mean, X composed Y and Y composed X are different here. The outputs in general will be different, right? Because which is very important for the entire point, right? So it suddenly makes sense to think about, if there's a notion of addition, you start to possibly think about commutators, right? In a very systematic way. But I'm getting ahead of myself. So okay, so the composition case, I think we are on the same page. Makes sense. Nothing surprising. It's just paths. It's just matrix adjacency matrix multiplication with labels. Blah blah. No problem. Okay, but I would claim that addition of vectors, and for this maybe one of these canvas makes sense.
I guess you also have to reverse the composition, right? If you have is it Y after X or X after Y in that rewriting rule?
In this one?
Yeah, it's Y after X, right?
Y after X? Yeah, it depends on your convention of where you put the dot.
Just small, yeah, side comment. Okay.
Yeah.
Let's go to addition.
Yeah. So addition, as you know, if what addition is the rule of the parallelogram, right? That's what everyone should have in their minds when they think about addition, right? Of vectors. Vector addition, not addition in general. Yep. Vector addition is the parallelogram rule. So the parallelogram rule is a situation where you can go in this direction and you can go in this direction, and that happens to be that you can go in this direction and you can go in this direction, and there's a parallelity property here, right? So parallelism makes sense in this context, right? So like people represent like with some lines or something, right? So okay, that's geometry. We don't have any sense of angle or parallel lines or anything like that in our context, but we do have a sense of building a parallelogram diagram, right? If you have X and Y as two different highlighted sub-directed graphs, then you can just ask, where are my parallelograms, right? Which are exactly this particular pattern, right? This left-hand side, where 1, 2 is X, 4, 3 is X, 1, 4 is Y, 2, 3 is Y. So in that particular instance, you say, okay, so that's X plus Y. If this occurs, then I have X plus Y, right? Which is funny because it's kind of more restrictive than composition, right? So it's kind of funny. I thought it was actually kind of funny that it's addition, which is always defined for vector fields, is actually more restrictive than composition in our context. Anyway, just funny thing.
Category theorists would disagree with that. It's like the composition.
Sure, well, of course, yeah, of course. I mean, of course. But I mean it in the context of vector fields, in the context of geometry, right? You have two vector
Yeah,
fields. It's almost like you almost never think of additions. Like, oh yeah, I can write plus and minus. Obviously, I learned that in preschool or something. And then composition of vector fields, like, okay, is that a derivation? Is that just a differential operator? Is that like, it gets mad. So in here is the other way around. It's like the composition is the trivial thing. Yeah, we know this. This is just categorical composition. No wonder. And addition becomes a little bit more sophisticated. So my claim would be that you have this you have this rule, so it's exactly the same idea. I give you two vector fields, potentially partially defined, blah blah blah. You do a one-pass rewriting with this rule, you get a new vector field. It might be empty, it might be whatever, but you get a new one. And that one I would claim is the addition of those two, right? And so the interesting comment here is that so these are the motivating examples. So the rewriting perspective that I have is that what if we just turn everything that you do on the calculus side, right? So adding things, multiplying things, composing things, tensor contraction, all those things. Now that they have graphic instantiation, it just reduces to rewriting. It's just there's some particular, you choose your rewriting rules carefully so that they represent what you want to represent. I mean, I don't know if you want this parallelogram rule. I drew it because it looks like the diagram from school.
Yeah, that's true. Yeah, it's also, I think, obviously commutative, right?
It is obviously commutative, yes.
It doesn't care. It's like,
Wait,
just
is that
symmetric.
true? Is that true? That's actually interesting.
But we still get the same kind of rewriting, but well, it depends what you're asking by commutative. Whether if you take this rewriting rule with x and y there, and the similar one when you switch the order of x and y, whether you after rewriting.
Oh yes, no, that's true. Yes, no, that's absolutely true. Yes. I know what you mean. Yes, that's it. That's right. Yeah, that's very good observation. It's commutative. Okay, so Martin is commenting, commutative addition and hypergraphs might have something to do with multi-way rewriting. Well, that's exactly what we are implying here. So good observation. To have a parallelogram, you need to have a fiber bundle. I mean, the parallelogram is construction in affine spaces. Fiber bundle, I mean, there are fiber bundle versions of that, but I don't think that that's necessary. But anyway, so this is kind of my two motivating examples that make me think of just running. So
well, we can make another obvious rule that just reverses the edge, and that's going to be just minus x.
Okay, that came to mind, I think, exactly at the same time I came to you, but I immediately suppressed the thought because I thought, wait, is that in some way reversing addition so that it's the negative? Is x minus is x plus minus x 0 in some sense? Like, there's no sense of doing minus if we don't have it.
Well, let's think about it.
Yeah, but let's think about it. No, I like it. Okay, so you're suggesting something like
x minus x. Let's
see if I can do it live. This is a test for the Padlet. Okay, so you want this, but you want it directed. Let's do some nice blue or something. Okay, and oh no, but obviously I'm using the. Oh, now it just returns this, and interesting.
Yeah, if you want to put like a new cell, that's the print.
Okay, cool.
More sense.
So yeah, I'm gonna beep, beep, beep. Edge label x. Ooh, you see that?
Yeah. Well, we can pan it around
Yeah.
maybe with the shift so that it's not on top of the print.
Oof.
Oh, it shouldn't. Well, I'm pretty sure that it shouldn't trigger on top of those buttons.
Well, it's definitely considering it's
I
selected.
definitely struggled with the dynamics there. It's like very confusing. I kind of got frustrated.
Anyway, let me just. Okay, this is wow. Now the notebook is crashing.
Yeah.
Anyway, so you're suggesting that reversing the order.
I'm just wondering what would happen if you make a x minus x field, by rewriting.
So,
if you have minus x, you obviously have this your edges inversed, and then if you
how do I delete everything here? You know, is that
everything? I think you should be able to select those.
it's super bugged? I think.
Just maybe double click it or something. If you can have canvas inside canvas.
Yeah, it just nested now.
Weird.
Well, I mean, the thing is, okay, so if you have a parallelogram like that, and this is x and y, right? Well, imagine that we have x everywhere. Then this is 2x. Is x plus x. So if I do minus in here, I mean, I should have called that y actually, because why not? Then this is reversed here, and x. Then
well, pretty confusing to me that you should do it to your left hand side, this transformation.
So it's basically this vector. So I think it's correct. I think it actually makes sense. I think it makes sense. Okay, so let me try and. So because you can say that if you have parallelogram like this with these directions, right? And this is x, and this is y, right? Then how do you change color? Whatever. Right? That thing there is addition. This thing here is difference.
Yeah. Is it? Well,
and
that's kind of, I get it, but I was just considering x minus x case, because it's not removing edges, you're only adding edges, right? So your vector field is always gonna contain an edges. So if you build x minus x field,
well,
what it's gonna do is
I mean,
basically.
The thing is, okay, so I see what you mean. So let me can I have it bigger? Can I?
Does that mean it's not gonna?
So how do I reset it? I don't want to. Okay, too laggy. Okay, I need to draw with my hands. So the thing is, in some vertices, I think, okay, so if you have vertex 1, vertex 2 for x, x 2, 1 goes to 2. Goes to 3. 3 goes to 4. I think, I mean, what I'm thinking about is if you have, yeah, let me see if this thing lets me draw.
I think there's like some kind of contradiction.
You think
Or
so?
is this?
I mean,
if you make this parallelogram with x and minus x, it's basically you can show that this kind of rule never applies or something like this.
okay, imagine this situation, right? This is just x, so it's just the same vector field, right?
Yeah.
So in terms of a symbolic rewrite rule, right?
Mm-hmm.
Which is a bit sketchy in here, what I'm trying to say. Then if your vector field has this 1, 2, x, 1, 2, x, 2, 3, then it also has this diagram, right? I mean,
Okay.
right? It's just a redundant expression of the
Yep.
same diagram. So obviously you can add it in this way, but you can also subtract it in this way. Which so this is x plus x, right? 2x.
Mm-hmm.
And this one is x minus x. X minus x happens to be 0 in our convention, right? I mean, this is what I have in mind. This doesn't make sense literally, because obviously literally is not the same diagram. So literally you don't rewrite just like that. But maybe this is teaching us something. I mean, maybe this is suggesting that vector fields should, like, the graph of vector fields, I mean, in some sense, that's right? I mean, if vector
No,
fields are,
can you draw those minus x field on those 1, 2, 3 path? Right?
with
It's going to
x,
be just arrows going backwards. That's going to be minus x, right? Or not?
well, I mean,
Like, is this?
so this x
This
is
is your
everywhere, right?
minus
So
x.
this x is everywhere. Oh yeah. I mean, you just change direction, but the argument applies because x minus x is the same as x minus x. Yeah. I think the point I'm trying to make is that what you define, this is the thing, right? What you define is not minus x, but, or maybe you do. And I think this is telling us that you should probably define minus x as you say, just reversing. But if you have x and y, you can define x plus y, and you can define x minus y. I mean, those are well defined, right?
Yeah. Yeah, I think so.
And so I think that's, yeah, I think that's what I was trying to say, right? This diagram, the parallelogram rule defines both x plus y and x minus y, obviously, right? Even if we don't have a, so Martin, so we are not, so these are edges. So there are no vector spaces, there are no tangent spaces here. This is graphic data. It is as simple as it gets. I mean, what you see is what you get, kind of situation. Okay, so x minus y and x plus y are equivalently defined, right? It's not. I don't think you can argue that one is plus and the other is minus because it's the negative of that. It's just two operations that are equally well defined with the parallelogram rule. What I find interesting is, I think, if you agree that this vector field is the zero vector field, or the zero value, right? The self loop is the R candidate for the zero value. Then when you draw this particular diagram, x, both, so x equals y and, vertex 3 or vertex 2 equals to a vertex 4 or something, right? Which is, I think, telling us something, telling that we should think of the graph of paths as a graph that is not the literal spatial graph, right? Which it's kind of what we're doing when we said that the tangent bundle is the set of all directed from the undirected. You remember that? I think.
Mm-hmm.
I think that's probably something that we should be considering. I mean, because then, if this is the case, if this diagram holds, then sure enough, you have x minus x equals 0, right? I mean, that, in the sense that if the vector field had all the diagrams like that, then it would be the case. And for any place where this happens, right?
It's just basically it's just a bunch of loops around the vertices.
Yeah,
That's
yeah. But I wonder. Okay, this is subtle, and this is probably a good sign. But this is getting subtle. It means that we're probably on the right track. That this is the right thing to do.
It's like what exactly you're writing, right? It's like, what is if you're given two fields, you first you need to, are you just rewriting your labeled original hypergraph with your left-hand side of your rule basically acting as a labeled rewriting of a hypergraph, so the labels are basically taken into account, or you're basically making some new kind of structure out of this two fields that you want to rewrite, and then just
exactly what
put
you
it
mean.
back into your hypergraph. Right?
No, I know exactly what you mean.
Like if your expression that you want to replicate using rewriting, you have to, it may contain multiple copies of the same field, like here. You're adding two x's, right? It maybe doesn't make sense to have it in the original hypergraph.
No, exactly. I mean, no, it does not make sense in the sense that I think that, so okay, this is a rule rewrite. So this is a rule application condition, right? I mean, this is a left-hand side for a rule, if you want, right? So we're not making statements about whether actually the vector field is 0 or anything like that, because it's just, I mean, this equality here is probably something like a rewrite rule produces an outcome and a rewrite rule produces an outcome, right? Like you can imagine that you have the 0 rewrite rule, which is like find all your edges and make them self edges, right? And that's like a rewriting process that you can do. It's a very trivial one, but it's one that you can do. And then you also have this process where you go, okay, go to your x and find these x minus x patterns, right? And maybe the statement here is that the result of both algorithms is the same, right? The result of both rewriting algorithms on your vector field data on your hypergraph, which is a graph on top of your original hypergraph. This we already know that this is not new. We don't have to create a new hypergraph in this sense because we already created a new hypergraph in this sense, that we had the original graph as basis space, and then on top of it we thought of directed graphs as paths or tangent bundles and all that stuff, right? So the question is how you define rules for pattern matching, right? It's not so much what graphs you're end up rewriting, because I mean this labeled hypergraph, right? This is a fully labeled hypergraph in the sense that I need to use normally, right? It's like 1, 2, and 3. They are tags for vertices. They just happen to share the name, right? So the diagram, you fully see the diagram when you make it into a parallelogram, but for that you need to duplicate some symbols. Just like when you compose with an identity, you need to make 2 copies of the same object, right? To write the identity arrow between them, right?
Well, I guess the confusing part for me right now is that usually I think we consider it, well, I did consider it at some point, but I think you didn't like this idea, that our left-hand side vertices should be able, when you do the rewriting, should be able to match to the single vertex, right? Like in this case, if you have a parallelogram rule on your parallelogram diagram on your left-hand side,
yeah.
those like opposite vertices should be able to match to the same one.
No,
Because
I know what you mean.
You don't even have to label them. They basically considered unlabeled. Every kind of pattern that you can find in your hypergraph, you should be able to rewrite, whether those vertices map to one vertices or two different one.
Yeah.
So
No. I understand exactly what you mean. I know that this is slightly different to how we've been doing rule rewriting. I mean, hypergraph rewriting.
yeah, there's basically different modes of rewriting. It's like
yeah.
I have it just as the names like tuple rewriting or orderless subset rewriting. In that
Right.
case, it would be
Right.
tuple rewriting.
Yes. So I guess there's an extra subtlety here that I completely agree with what you said, but there's an extra layer of subtlety that I just noticed, which is that according to this, right, if this is the situation that you have x 1, 2, 3 like that,
Yeah,
it seems that if you do x compose minus x, it seems that that's also going to give you 0. If minus is reversal of direction, right?
yeah.
Which I'm not 100% convinced yet that it should be.
Yeah, so some kind of involution. There may be multiple definitions for those, multiple versions. Yeah.
I don't know how else you can do an involution with a directed edge, to be honest.
I don't know.
But yeah, this looks it's
Well, maybe we need to consider edges as places. Maybe it's gonna resolve this issue.
Yes, that will be the solution for sure. Let me just, for completion, I want, my completionist brain wants to see. Oh dear, just copying this and making it slow.
Can you just regulate it in place? Do you want to just better labels there? Or...
No. These are just the input.
Yeah.
Wait. So I can just do this. All I wanted to change was x minus, and it goes not 1 to 3, but what? X, y, x minus y, then it should end in x. So then 2, 4. 2, 2, 4 here as well.
I'm trying to make a rule for x minus.
Yeah.
To mine. Why are you changing left hand side then? Is it left hand side?
No, it's the right hand side.
Oh.
It's out.
So yeah, sure. Okay.
What? Oh, because they have the same names. Wait, but sum in.
Can you evaluate it in place just to be sure? Well, we still have the edge there. 1, 3. That's the important part. Right here.
Yeah.
2, 4.
Yeah. And 2, 4 here, right? But I just have to. I also have to change the name, right?
Yeah.
Cool. Is that right? X minus y. Yes, that's right. So laggy. I don't know why. Yeah. Anyway, that was the subtlety that I was thinking of. That composition. I mean, the negative, it makes sense. But, okay, so here's the problem, right? So that negative seems to be the flow negative. That negative, that reversal seems to be more clearly the compositional inverse, right?
Mm-hmm.
So, okay, because we had to go through this complicated thing, like inventing maybe a rule application is not the same, and we have to do it in some kind of path graph that is different, blah, blah, blah. Like doing like labeled vertex kind of rewriting. But with composition has no distinction, right? There's an actual minus, which we should probably call like bar or something, which is the opposite flow, which is like flow with minus t, right? Flow with negative time in the flow picture. So I think it's well defined. I mean, I think it's a well defined operation, obviously, but I think it's the opposite of is the compositional inverse, right?
Right.
And
the additional inverse or summation inverse is not maybe not
well,
clear
the thing
yet.
is, they are not operations, right? So it's just notation that we call them class. It's just kind of a traditional name that we give them because they are evoking that, or they come from that, or they reduce to that. Maybe in some situations we can prove that, but in general, they're not going to be operations. So it's not that, I mean, I think it's a meaningful question to ask, right? Like, given an x, can you find the y such that x plus y equals the 0 vector? I think that's a meaningful question. I mean, sometimes it will exist, sometimes it will not, right? But to say that given a y, here's the strong difference of these two statements, right? So one is, given an x, can you find a y? Or let me say, can you find an x prime such that x minus x prime equals the 0 vector? That's a well-defined question, right? But it makes sense. At least partially defined vectors, whatever it's defined, it matches the equation, right? Note how different the question is when you say, for any x and y, when you compose x plus minus y, where minus is this reverse, you actually get the 0 vector. That's much stronger, right?
Yeah.
So that's why we don't have one. That's good. That's good. Okay, we got it. Like, this makes sense. I mean, it's kind of a. So I should vector field complete. I'm just gonna add. Well, what? Don't tell me you crashed. No.
Well, anyway.
Yeah, no, but this is so
For me, it's kind of
frustrating.
weird that you can define both plus and minus, but can't.
You find it weird?
Yeah,
I don't
think
find
it's
it weird
like
at all.
you can compose them, right? To make an actual minus operator.
Can you?
Should be able. Should be. It's like you either define a minus or difference, usually. And
Well, but it's a usual thing in like the Grothendieck construction, this semi-group, the semi-group construction, right? That you define an operation between differences. You don't really have subtraction. You can only really add, and so you develop this theory of differences, like what you think will be differences, right? It's like the definition of the integers. Right? If you have the naturals, oh, it didn't crash.
if you take your subtraction rewriting rule and replace your x on the left-hand side with a loop, with a zero vector field, you basically should be able to get the rewriting rule for taking minus sign of your vector field.
Say it again. So you take the rewriting rule that sends any vector to the 0 vector?
No, just on your left-hand side of your parallelogram.
Yeah.
Replace your blue x arrows with the loops that represent a 0, right? And that's your rewriting rule should be able to take your arbitrary y field to its minus. No? If you're going to define it like that. If you have a definition for the 0 one and you also have a definition for difference, then it's should define the minus.
Sure. I mean, but that's where we get, okay, but then we are firmly back to the weird, what does it mean to rewrite thing? Because if you have loops, then the rewrite rule is not going to apply explicitly unless the rewrite rule is fully symbolic, right? In which case you would have to write, 1, 1 for x, which is 0, and then 2, 2 for x, which is 0, and then y is from 1 to 2 in both cases, right? You know what I mean?
Yeah, I guess.
It's like in this diagram, right? X will be 0, so that you have minus y. So you have just minus y, 0 minus y. So then you would have to have this to be self-loop y, self-loop, right? Or if we're not allowing self-loops in the rewriting, which was my point and all the way, right? Like I always said, we shouldn't have self-loops in the rewriting because the rewriting has labels that allows us to do loops with the labels, right? Then you can use the same diagram, this one diagram, but using the vertex labels 1, 1 and 2, 2, right? But again, it's not gonna, I mean,
I don't know. I don't know. I'm too tired. It's like it's very confusing. It's like it seems even undefined at this point.
well,
It's like
it's
how you would choose vertex 2 if your X is a loop. It's like
well, but
why would
that's
you
what I
choose?
mean. That's exactly what I
Yeah,
mean. So
yeah.
what I mean is that, yeah, so okay, give me a second. So if this is 1 and this is 1, this is 2 and this is 2. What direction is it pointing? That's annoying. Is it pointing down or up? Down. Is that correct?
No.
That's not correct. It's the other way around.
You should yeah. You
Yeah,
switch the arrow.
exactly. It should be the other way around. I mean, let me just change this.
4 to 2. I'll just change the label here.
Because I like y minus x better aesthetically. Okay, so y has to be 0. Okay, this makes sense. So this makes sense. This works actually.
Yeah.
Because, I mean,
Right.
let me annotate on top. I need to annotate on top. So this is 1. This is 1. Ah, terrible color. Right. This is 1. This is 1. And this is 2 and this is 2, right? If we're doing the labeled rewriting. And so if this is 0, that's 0. I mean, if 1 is 1, you know, if the labels are like that, that's the 0 vector by definition. Then this rewriting indeed gives you an edge that goes from, so, you know, this edge was from 1 to 2 in this way. This edge is from, you know, if I put 1, 1, 2, 2,
Yeah,
that arrow
makes sense.
is going downwards, so it's 1 to 2, right? So it works.
Yeah.
It works. It's very strange though. We have to make sense of this. This is very strange. But I think it's making sense, right? Like in some weird way, this is speaking the language of correctness, right? Like it's somehow there seems to be something here that is making sense. But anyway, maybe we can close it there. I think I have enough notes here that I'll remember everything, and maybe next week we can chat with Jonathan, and we can delve deeper into this, because I think this has future. I think this is I mean, Stephen might not know it, but I think this is what Stephen wants.
Okay.
Because, I mean, at one point he said explicitly, I want something that replaces calculus. He called it infracalculus, right? Like he wanted something that, I think this is exactly that, right? Like you are calling your things plus and minus because you just come from the tradition that you interpreted, blah, blah, blah. But, you know, in reality, all you are doing is just hypergraph rewriting. That's all you're doing, right? So it looks good. It looks pretty good. So how do I... Okay, so let me just copy this and we close the stream. Oh no, I'm not gonna be able to. Whatever. It's so simple, right? No, it's not even liking. So when you do this, will this work?
Why not? Should.
No, how do I make directed? Is it here?
Well, the edge symmetry.
Edge symmetry as an option, right?
Yeah.
Like that?
Ordered.
Sure. So this is simple as P1. Read out. Graph. Oh, and the label? That's labels, right?
Edge labels.
And then I do the like
1,
that,
2, arrow. Oh, those are crazy labeling. The distance is weird.
Yeah, doesn't matter. Okay, but yeah, that's the rule. And okay, just for symmetry, if I say vertex labels automatic, yep, that's what I wanted. It's a bit too close. Yeah, placing is a bit weird.
Well, you can place it manually if you want.
No, I mean,
you can wrap your X with placed and then specify
no,
actual
but
offset.
I mean also the edge label, the vertex labels, super close,
Yeah.
right? Why is it? This distance is different.
Well,
This copied from the draw, right?
well, it's a single edge. It's just the way I'm computing how much, like, what is the offset from the actual center is very stupid right now. Maybe it depends, like, maybe on how many vertices there are.
Right.
And the actual size of the whole graphics.
Right.
Because, well, it's absolute, not relative. I guess I have to change it. Relative to the size of the graphics.
Okay, yeah, no problem. That's fine. Okay, so yeah, it's very good. That's very nice. Okay, label and really. This is neat. So we have some candidates for interesting stuff. Anyway, I think it's a good place to stop. And yeah, we can be in touch next week and carry on. Because today was super productive. I mean, we discovered the edges as places, and we have to follow down that rabbit hole, because things are gonna, yeah. I don't know how I mean, suddenly I guess it's just the nature of, because if you can have paths that are edges, directed edges. Okay, I don't know. It's hard to like, because this picture is quite intuitively clear. If 1, 2, 3, 4 are places, and X and Y are ways to travel between places, right? Then the interpretation of what you're doing is very obvious. It's like, okay, yeah, I know exactly what I'm doing. But if I have to now think that, any edge is a place, and, composing paths is like some kind of hypergraphic rewriting. Like, I don't know. But anyway, I think at the end of the day, what we want is to recover calculus, and calculus should just be rewriting of the graphic structures themselves that represent some kind of property of the space itself. So I think we're on good tracks. But anyway, yeah, thanks very much for the session. That was very useful.
Thanks. Thanks, everyone.
Yeah, thanks
Thanks
everyone.
very much.
See you soon.
Thanks, Carlos.
Goodbye.